Hello students, this is Professor Chalai, and in this video we're going to look at light as a particle. As always, you can follow along with our Chapter 6 workbook. By the end of this video, you should be able to describe a photon and also relate the energy of light to its properties like its frequency and its wavelength. Let's get started. So I would like you to read your textbook before you begin this video if you haven't done so already, and in your own words, describe the ultraviolet catastrophe and the photoelectric effect. Both of these are experiments and observations that led to the idea that light is not only a wave, but also a particle. Now, you might be asking, what do I mean when I say light is a particle? Because we have an idea now, based off of what we talked in our previous video, of what waves are. We have an idea of what waves are, but what do we mean by a particle? Well, particle is just a fancy word for sort of a piece, any solid, if you will, piece of matter. So you can model, for example, like a ball, a baseball, a basketball. That's a particle, a very gigantic particle. And it moves in ways that we could understand based off of, classical Newtonian physics. So if you throw a ball up and it reacts with gravity, it comes back down, it bounces off of things in very predictable ways. And so that's what we mean by a particle. You can imagine as like a solid ball that's very, very tiny. When we call matter particle, we use this word particle. So oftentimes when you might imagine atoms, you might be imagining tiny little balls zipping around or connecting in various ways. So yeah, that's what we mean by particle, and that's what the behavior of a particle is. What we're going to use to model light in this video. So these little particles of light, after we've discovered that they exist based off of the ultraviolet catastrophe and the photoelectric effect, we've come to call a photon. So a photon is simply a particle of light. So you can imagine a light, such as the light coming from your computer screen right now, as composing of billions and billions and billions of these tiny particles, like tiny balls shooting out of the screen and hitting your eyes. Okay, so what this means, based off of all of these observations, like we see in the previous video, and now what we've read about these effects, is light can be treated as both a wave and a particle. And so this is what we mean when we say light has a wave-particle duality. Light can be treated as a wave, it can be treated as a particle, it exists, it exhibits properties of both. Why it does so exactly is not quite understood. Just know that it does. People are still trying to figure out what exactly we mean by a wave-particle duality, or rather, what does a wave-particle duality exactly mean for light or electrons, as we'll talk about later in this chapter. But just know that light has a wave-particle duality, and as we'll learn later, electrons also have a wave-particle duality. Okay, so if light is made up of these tiny little photons, we can actually calculate the energy of every one of these tiny photons using this equation right here. So the energy of each of those photons is this h times the frequency, this constant h times the frequency, or this constant h times the speed of light divided by the wavelength. Because we know that since the speed of light is the frequency, wavelength times the frequency, then the frequency is equal to the speed over the wavelength. So this here is just the frequency. So it's h multiplied by the frequency. We know that from our previous chapter that energy is in units of joules, frequency is in units of per second or hertz. So this means that h should have units of joules per second. And here is the value of h. H is just called Planck's constant. And the value for Planck's constant is going to be 6.626 by 10 to the minus 34 joules times seconds. Sorry, I misspoke up here. It should be joules times seconds, so that seconds will cancel out when you multiply them, and you'll just be left with joules. There we go. All right. So that is the energy of the photon. So every one of those tiny little photons that exits your monitor and hits your eyes so that you can see this video would have a tiny amount of energy that we can calculate using this equation. So if we have the frequency of the light in per seconds, we can multiply it by Planck's constant to get our energy. If we have the wavelength of light, right, we can use this equation to calculate the energy of every one of those photons. Okay, with that in mind, you can go ahead and answer number 5 on your own. Number 5 is just relating the frequency and the wavelength of light, so you should be very comfortable doing this. And using the equation for the energy of one photon, try to answer number 6. So we have 1 photon of blue light and 2 photons of red light. You might expect that blue light has more energy than red light because it has higher frequency, and energy is related to frequency. But does 1 photon of blue light have more energy than 2 photons of red light? So try to do the calculation on your own, and let's see what answer you come up with. Okay. Hopefully you've tried to work this out on your own, but and you came up with the right answer. But let's see what you get. I'll use blue colors for blue light because why not? So we know that 1 photon of blue light will have energy equals to h times c over lambda. I'm using this form of the equation because they give us the wavelength, right? H is 6.626 by 10 to the minus 34 joules times seconds, right? The speed of light is 3.00 by 10 to the 8th meters per second, so ms to the minus 1. And the wavelength of light is 450 nanometers, but nano means 10 to the minus 9, so I'm just going to rewrite this as 450 times 10 to the minus 9 meters. And that way, seconds cancel with per second, meters cancel with meters, and we're left with answers in joules. And the amount of joule that you should get from this is 4.4 by 10 to the minus 19 joules. So pay attention to this sort of order of magnitude, 10 to the minus 19 joules. That's about how much energy you can expect for visible light, like within the visible spectrum. If you get numbers for visible photons that are very different from 10 to the minus 19, like 10 to the minus 25 or 10 to the positive 25 or something like that, you are probably doing something wrong. So this 10 to the minus 19, that's a very, very small amount of joules of energy, but it's just 1 photon, right? So there are lots and lots of photon hitting you at all times. Okay, let's figure out the energy for 2 photons of red light. So 1 photon will have h times c, whoops, what's happening here? H times c, c over lambda for 1 photon multiplied by 2 for 2 photons, right? H again is 6.626 by 10 to the minus 34 joules times seconds. Speed of light, as always, or in a vacuum, is 3.00 by 10 to the 8th meters per second. And the red photons have a wavelength of 700 nanometers, so that would be 700 by 10 to the minus 9 meters. So per second cancel it per second, meters cancel it meters, and we're left with joules. But we have 2 photons, so we need to multiply this by 2, and so the energy that we get from 2 photons of red light, if we punch all of these into our calculator, should be 6 by 10 to the minus 19 joules. So look at that. 2 photons of red light has more energy than 1 photon of blue light. And of course, it depends on the exact frequency or wavelength. Just remember that whenever you're punching these numbers into your calculator, just put parentheses around them because sometimes some calculators can make the answers wonky. Okay, try number 7 on your own. It's using the energy of 1 photon in an interesting way to find how many photons of yellow light you need for 1 joule of energy. 1 joule of energy is still a tiny amount of energy, but how many photons of light would that be? See if you can try to figure this on your own. And then if you when you're done, unpause the video and I'll go over it with you. Okay, so we know that 1 photon of yellow light has energy h times c over lambda, right? Because they gave us the wavelength, so we use the wavelength form of the equation. And if we multiply this by, let's call it x photons, we should get 1.0 joules of energy. So we need to find how many photons that would be. So the x number of photons should be equal to 1.0 joules divided by this quantity here, which we'll just call the energy for yellow light. So we'll call it energy for yellow. So we just need to find the energy of one photon of yellow light. So let's do that. The energy will be hc over lambda, which is 6.626 by 10 to the minus 34 joules times seconds. C is 3.00 by 10 to the 8 meters per second. So second and per second cancel out. And our yellow light is 590 nanometers. So that's 590 times 10 to the minus 9 meters. Nano is just 10 to the minus 9. So meters cancel out. And I get an energy of about 3.4 by 10 to the minus 9 joules. So let's use this energy here. 3.9 by 10 to the minus 19 joules. So that joules cancel out, and the number of photons that we end up with is going to be 3.0 by 10 to the 19 photons. So even 1 joule of energy, which is a very tiny amount of energy, has a ridiculously large number of photons. That's 3 with 19 zeros behind it. That many number of photons. Okay, so this brings us to the end of this video where we talked about light as photons. And we use various calculations using the energy of a photon and Planck's constant. In our next video, we're going to talk about the Bohr model. We'll see you then. Bye.